Okay, good morning everyone, and thank you for joining today's WASP webinar, where we look at how autonomous vessels could be integrated into future operations for offshore wind farms. So I'm Simon Cheeseman. I lead the Offshore Renewable Energy Catapult's activities in the southwest of England and also in East Anglia. This webinar is being recorded and you'll be able to download the recording, including the presentational material, at the end of this broadcast from the Offshore Renewable Energy Catapult website. First of all, I'll ask Steve Pears, Managing Director of Sea-Rock Group, to introduce himself. Good morning, Steve.
Good morning. Thank you for the introduction, Simon. I hope you can hear me okay.
Yeah, fine. Perfect, Steve.
So the Sea Planner, which is part of the Sea-Rock Group, was very much involved with the sort of research and development, looking at the carrying out desktop studies and talking to some of our clients to understand what the problems could be that the autonomous vessels could solve. So the slide in front of you shows the different cases that we looked at. We focused on what we considered to be case number one, which was delivering the actual cargo parts. So Sea Planner is a software system used by many clients for managing their vessel and people operations. So that put us in a very good location to integrate that capability within Sea Planner.
Okay.
Is that enough?
Yeah, that's fine. Thanks, Steve. Can I next ask Jamila from University of Portsmouth to introduce herself? Jamila.
Hi, thanks, Simon. Hi, good morning, everyone. I hope you can hear me.
Yeah, I can hear you fine.
So I am Jamila Walad, and I'm Professor of Operational Research and Analytics at the University of Portsmouth. Our work on the WASP project has focused on logistics management and optimal route planning for spare parts delivery in offshore wind farms. We have implemented optimization models and intelligent computational methods to actually generate real-time routing to increase journey efficiency. And of course, those models and intelligent algorithms take into account information on the constraints around the vessels, the autonomous vessels, and the cargo, and as well the weather and sea conditions. Is that enough, Simon?
That's perfect for now, Jamila. That's absolutely perfect. Yep. Next on my screen, I'd ask Aaron Pillai to introduce themselves. Morning, Aaron.
Morning, Simon. Thank you. Can you hear me? Hello?
Yeah, hear you perfectly.
Hello, yeah. I'm Aaron Pillai. I work with Holder Limited. I'm a principal engineer and project manager for this project. I work for Holder. As part of this project, we kind of brought together the vessel design, that is the autonomous surface vessel, which had the functional requirement of delivering cargo to the wind farm to support the wind farm O&M, scheduled maintenance and scheduled maintenance. So brought together the vessel design, the equipment design, and our tailored analysis to deliver this autonomous surface vessel with its motion compensated cargo arm. Thank you.
Thanks very much, Aaron. And hopefully we've got James Cowles from L3 Harris. James, are you there? I can't see you on my my panelist screen.
Oh, I'm here. Don't panic, Simon.
Okay, panic over. Good to see you, James. Would you like to introduce yourself and your company?
Yeah, I'm James Cowles from L3 Harris, formerly known as ASV. We have been developing autonomous vessel technology for the last 20 years and deploying it around the world. Now, as part of the larger L3 Harris group, within this project, we've been looking at how we develop the actual autonomy of the vessel to ensure the safe operations, looking at things like collision avoidance, operations, and how we follow the appropriate track as fed in by people like Sea Planner and things from the University of Portsmouth as well.
Okay, that's great. So that's all our panelists assembled now. So what you see in front of you, this operational concept, was the concept that we finally fell upon for WASP. If I go back a slide, you can see here there's a number of opportunities. We could look at robotic delivery systems, number one in the center of the screen there. Off to the right, we could have looked at sort of geophysical surveys that vessels could carry out. That's becoming fairly routine now. Up in the top left, sort of security operations to maintain security around a wind farm that's being built or is established to stop sort of drifting craft or offshore fishing. We could have looked at crew transfer. So those were the sort of areas that we looked at, but we felt that looking at robotic delivery systems was actually one where we could encompass a lot of other features. So any autonomous platform needs to know where it is at any sort of time. It therefore has a view using its various sensors of the sort of recognized sea picture. So it provides you a sort of security application anyway. Later we'll talk about sort of multi-role vessels that could also at the same time be doing other tasks, maybe monitoring subsea cables, maybe monitoring scour, as well as doing the sort of delivery system. But I suppose first of all, we ought to just get the vernacular sorted out and look at terminology and just think about what sort of vessels are out there. I tend to slip into talking about autonomous vessels straight away, and quite often James will pick me up on that and will say, well, they're not always autonomous. There may always be someone else in the loop actually controlling these things and dialing in and out the level of autonomy. But maybe James, do you want to sort of just talk us through the terminology that you feel comfortable with in terms of describing these sort of systems?
I think predominantly the phrase that people would use is unmanned. So primarily all of the vessels that we build and have involvement in build and the things like the Holder designed are unmanned. So they don't have people on them. And now part of what they will do will be autonomous, but part of what they will do will be remote control. So I think from that point of view, I think unmanned is probably the best way of looking at it. And also looking at it from a point of view of some of what they're doing will be autonomous. And as we move into the future, that level of autonomy and the degree of time that they'll be autonomous for will increase. So we'll be looking at the moment, we would probably drive manually out of port from a remote location, but manually. We would then allow it to transit autonomously, where we'd engage a collision avoidance, and it would manage to avoid, it can avoid pretty much anything in its way as long as they are following broadly the rules of the road. And if they're not following the rules of the road, then it can take an evasive action further on from that. And then as we move to the future, more and more of those operations will become fully autonomous, like leaving ports, for example, teaching our vessels around things like what a channel is and how you follow it is a critical part to how we get to that more autonomous operation. Does that help answer your question, Simon?
Yeah, no, that's brilliant. I think it's important that we sort of understand what's sitting behind the sort of terminology that we use. So let's look a little bit more at the sort of operational concept. So in offshore wind farms today, what we traditionally have is small scale spares are brought to an offshore wind turbine by technicians traveling on a crew transfer vessel, and that crew transfer vessel then needs to push up against push on bars and a ladder, and the technicians then do the sort of the leap of faith onto the ladder, climb up the ladder, and then use a crane on the transition piece to pull up the tools and equipment they need to carry out the job, including any small scale spares, electronic items, that sort of thing. And invariably, the trouble with this is that you're restricted by weather windows, sea conditions. Human nature means that sometimes you may not bring the right tools or equipment, or the technicians may feel unwell once they get to the offshore wind turbine. So all these things can hamper operations, and Sea Planner in particular are very close to these sort of operations, and have a lot of anecdotal evidence in terms of the problems that are faced. And I wonder, Steve, if you'd like to sort of share some of that sort of anecdotal evidence of how difficult it is actually to coordinate getting the right people and the right tools in the right place at the right time offshore.
Okay, thanks, Simon. So there's been a lot of changes over the years from using spreadsheets and standalone radio systems to integrating the process together. But it comes down to the fact that clients want their turbines operational as much as possible. So any downtime on the turbine will outweigh some of the additional costs. So the effects that we have noticed is the failed transfers from vessels pushing on, and the number of trips out, especially far offshore projects, where you're taking out a number of technicians only to turn around and bring them home again. So there is transfer, but there is also the time to actually get all the equipment from the vessel onto the transition piece using the davit crane. And I would say the one key point that we learnt from this project is when we were talking to our project sponsor and we were looking at automating the davit crane, it was clear to us that they would prefer that there was no davit crane there at all, and because of the levels of failures of the davit cranes as well. So one of the things that we've learned is that our clients want to make things as simple as possible and to optimize the time of the technicians actually carrying out the repair. Is that enough for you, Simon?
That's brilliant. Thanks very much, Steve. Obviously, panelists, if there's other comments that you want to add, then feel free to chip in. So really, jumping to the sort of the solution that we arrived at was really a fairly large autonomous vessel fitted with a remote cargo delivery system that would enable the delivery of small-scale spares out to an offshore wind farm in a much wider weather window than was achievable at the moment. Here you can see a schematic of the design, and I need to pay tribute to Holder now, who sort of worked on this design, and I'll ask Aaron to tell us a little bit about more about the design. Aaron.
Thanks, Simon. Yeah, so based on the functional requirement that the initial research from Seaplaner and University of Portsmouth, both primary and secondary, chalking out that space for the vessel, as Simon alluded to as well. So that was a starting point. So we kind of homed in on further details, as also in discussions with our sponsor, Ørsted, who kind of helped us evolve these functional requirements into something more practical and concrete. So that's how it started off. So on the vessel now stands at around 29 meters, around 9 meter broad breadth, and around 320 tons of displacement. So that's where, and this has taken a fair bit of evolution and iteration to get there. We started off as rather small at 24 meters initially, just keeping it in line with the crew transfer vessels of the time. So that's where it started off. And then we kind of also did an optimization exercise, so to speak. We're trying to change the vessel shape and size to see what benefit can be accrued from the changes to vessel motions, because we are looking at putting a fairly large crane for that size of the vessel on the vessel to enable the scheduled maintenance for operation maintenance. So just going through the initial bits about what it does. It does deliver the small cargo delivery, which is a classification that's out there, and it's been cleaned out and refined by University of Portsmouth. So we looked at that 1 ton and less cargo delivery. So that will be, and this is not to replace any of the SOVs or the CTVs or the offshore bases on the wind farm at the moment. This is supplement it. what it does is it decouples the crew transfer and the cargo transfer, improving the safety of operation. So it removes the interface with on the vessel and also at the davit crane. So on the aspects of what are the other things about the endurance. So the vessel range actually was for a Hornsea light development around 120 kilometers from the diesel bunkers was sized for that. The endurance was for 4 days, which was again vetted by Austin as something that fits in with their planning window. So the vessel has kind of delivers around 40 tons of cargo, and we have gone for standardized cargo for now for a 1 square meter footprint or 1 cubic meter container, which would be standardized as the industry now uses a fairly large number, a varied size and number of cargo pallets or side boxes. So that deliver around 40 tons of carriage, which is more than sufficient for the planning window of the operators for the O&M. So that is the cargo payload. The motions we talked about. The other thing when you're coming into the space is, of course, one of the main things that as a designer you get the freedom is to do with the spaces, because you wouldn't need many of the spaces that you would traditionally associate with the vessel design. So there's some changes to real estate on that one. You would see that the accommodation module is conspicuous by its absence. We have a shelter area for maintenance crew to come in, and then we have redundancy of spaces provided, obviously to increase the reliability and serviceability of the machinery, and also to improve the safety of operations. We, as part of the design, we did an initial estimate of powering machinery system, thinking about the type of machinery with diesel, electric, hybrid. Intact and damage stability assessments, preliminary assessments were carried out, and an initial crane concept, which we'll come to later, was done as well. So that's a fully motion compensated cargo handling system for the small cargo delivery. And this is fully integrated and coupled with the vessel and just made designs bespoke for this vessel in question. The primary function I mentioned, that was about cargo delivery of this small cargo. We also looked at the survey and security options can be added, and we have the space availability within that and into the integration of systems to it. The limits of operation has been defined by stability and cargo handling. That's part of the analysis that we did. Is that a fair, and that's an introduction?
Yeah, no, that's great, Aaron. Can you tell us a little bit about the propulsion system? I mean, is it a DP capable vessel?
It is a DP capable vessel, yes. We've considered, the propulsion system is diesel electric. As we said, we have experience of having designed and delivered ferries with diesel electric propulsion systems. So we've adopted that. The hybrid system, and the azimuth propellers and with redundancy there, and we have 2 machinery spaces at the aft end, and we also have tunnel thrusters in the forward to provide additional maneuvering and station keeping capabilities. As we are designing this to be a DP2 capable vessel, the requirement of which so that should enable us to compensate. As we said, that's a motion compensated system. The motion compensation for the vessel is for the first order wave motions. It's been assumed at this stage, at the feasibility stage, that the DP takes care of the drift of the vessel system. Going forward, as we develop the prototype and test it, we will be testing for those for the actual drift of the vessel, for its design, and how that will couple with the first order motions, and how the compensation will work on that.
Can you explain the reason why you went diesel electric and not all electric? Was it to do with weight of batteries or endurance capabilities or thinking about recharging?
I think a whole lot of those, I think my colleague, the principal marine engineer here, David Pugh, and for him, it was, we wanted to go for something that's out there, which you can really adopt as part of the design. And we were fairly confident about diesel electric, and the battery, the use of that for 4 days, and the battery sizes, we were not quite sure of whether technology is available at this point to do that. And also the infrastructure, as you mentioned, about the recharging, all of that would have added to the complexity. And we wanted to look at the autonomy and how the vessel design relates to autonomy more than go into what should we say, still up and coming, the battery, the fully electric powering.
Okay, that's great. Thanks very much, Aaron. I mean, here's a sort of an artist's illustration, if you like, of the arm in motion. I think the key thing to think about now is that this vessel can approach that transition piece from any angle. It's not bounded by the need to push on to where the ladders are. It can approach now to suit the prevailing wind and tide conditions as well. Aaron, can you just tell us a little bit more about that concept for that robotic arm? What's the sort of reach that we're talking about? What's the sort of payload that it can deliver up onto that transition piece?
Yes, it is. The payload is coming out of the functional requirement of the vessel, so that it can deliver a maximum 1 ton of standardized cargo to the transition piece from the deck of the vessel. The deck, as you know, is a clear deck with the cargo stowed aft of midships. So from there, the vessel, the crane can pick up the cargo and slew around, go up to the transition piece, which we have assumed for the purpose of the design at 20 meters above the mean sea level. And the standoff distance from the transition piece is assumed as 5 meters. So that gives it around, so 20-meter height, plus you have the rails of the transition piece to overcome as well. So 20 to 22-meter height and 70 to 20 meters reach is what you needed for that. Given that it's a 30-meter vessel now, and plus, you know, the 5-meter standoff distance that you've assumed. So that's 20 meters outreach at more 20 to 21-meter high, and that's the actual the crane radius and function.
Yeah, and I suppose the challenge is that as the vessel's moving around all the time with the natural swell, or the waves that are out there and reacting to the wind, it's got to keep that payload, synchronized with the platform that it's actually going to, deposit the cargo onto. But just sort of before we go there, I'd like to bring James Cowles back into the conversation and ask James, how did the vessel get there? What are the navigation challenges that it's had to face, in this scenario, traveling sort of 120 kilometers offshore to the Hornsey 1 site to deliver that cargo? What are the things that you as a vessel designer and command and control sort of specialists, what do you need to take into account to make this happen?
Yeah, I think really interestingly that a large chunk of the actual voyage is quite easy. So when you're about three kilometers offshore and about a couple of kilometers outside the wind farm, that large majority of that transit is quite simple. You've got a lot of sea space to operate in. From a vessel of this size, you're going to have situational awareness out to potentially tens of miles. You'll know what's going on around you, which makes it really easy to plan where you're going to go and to avoid any potential hazards and operate effectively. What's really the challenge, and one of the things that we've been investigating throughout this project, is how you operate in that more constrained environment. Part of the challenge of the offshore wind farm is that because of its general grid arrangement, that really forces certainly manned vessels into relatively predictable but sometimes contradictory paths. So they'll go down the rows or up the columns effectively, and then change direction at certain points. And it's quite hard for the autonomy to necessarily predict when they're going to turn, because we won't have any information on where they're going. We'll just have to guess. So that does create a challenge for the autonomy. Then when you're in the port end of it, obviously you're even more constrained. But actually one of the benefits of the port environment is that where people are going is going to be much clearer. So part of the developments we've been looking at is how we define which vessels are in channels, and if they're in a channel, what channel are they in? So the example that we looked at was the Solent. So you could detect by looking at vessels AIS that if it was a car carrier, you can be pretty confident that it's going into Southampton or coming out of Southampton. And then by doing that, you can project that route onto the contours of the seabed around that area. And from doing that, you can predict a lot further into the future where vessels are going to be. And then by having that prediction much further into the future, that enables the autonomy to plan better. And that's always what you're looking to do. You want to know where you're going, not 5 or 10 seconds in the future. You want to know where you're going 5 or 10 minutes in the future, so that that enables you to operate an autonomous vessel in much the same way as you'd operate a manned vessel. One of the core principles of the collision regulations is being able to make an alteration to your course clearly and early. And without clear predictions, you're unable to do that. So part of the core challenge of getting a vessel safely and autonomously from shore to a wind farm is that ability to predict. And as I say, in open water, that's relatively easy. In constrained environments, it becomes a greater challenge, and that's why it's really been the focus of our developments within this project.
Brilliant, thanks, James. James, can you just tell us a little bit more about what sort of sensors would be on the vessel then? You know, what have we got in terms of, and what are we trying to integrate in terms of sensor technology to help the vessel understand where it is and make sure it doesn't collide with anything?
So we have 3 core sensor technologies that we use predominantly. That will be AIS, which is more used for gathering of data about what's around you as opposed to really predicting where it is. Radar, which is our primary method of detecting where something is, how it's moving, and therefore what level of hazard it presents to our vessel. And then the third one is cameras. Now, at the moment, cameras are not actively used for collision avoidance. They're more used for the operator's situational awareness. But we are developing technology to enable us to use the cameras to position vessels. So an example we've demonstrated today is if you put a QR code on the back of a vessel, you can follow that vessel around at a set distance and a set angle. And that would be extremely useful for positioning near a wind turbine, for example. We'd be able to position the vessel very accurately in terms of angle and distance by just using a camera. So that's going to become a critical sensor. And the other thing that the cameras are going to be doing is classifying some of the targets that the radar is picking up. One of the great challenges in collision regulations these days for autonomous vessels is the conundrum of sailing vessels with their sails up and sails down. You can tell it's a sailing vessel if it's transmitting AIS, and to an extent from radar you can tell it's a sailing vessel because of size and speed and things like that. But you can't tell if it's sailing. And obviously in the collision regulations, if it's sailing, you've got to behave differently as a motor vessel. So that's an interesting challenge for us. It's one thing we're looking at. The other side of that is how we detect vessels with day shape, night lights, so that we can ensure that we're adhering to the widest possible range of the collision regulations as opposed to just the classic of avoiding collision. Okay. So yeah, I hope that made some sense on the sensor front.
So not quite ready to sail one of these through the round the island race at the Isle of Wight then? Not yet.
I would say that would be a bit of a challenge for a number of reasons.
Jamila, obviously we've talked in terms of the a relatively simple operation of getting one vessel to one offshore wind turbine, but obviously the arrays have multiple wind turbines, often hundreds, and in terms of working out the optimum route, can you tell us a little bit more about the sort of algorithm that University of Portsmouth developed to try and solve this sort of very tricky sort of logistics problem? You're muted, Jamila. You need to turn your mic on.
Sorry.
Thank you very much.
Thank you. The way the optimization algorithms for route planning works, basically we receive requests from cPlanner on the turbines that have to be serviced with spare parts. Then we take those requests and we use, of course, the constraints around the autonomous vessel, the cargo. We have to take into account as well the weather window, the due dates when the vessels have to be serviced with spare parts. And then we take all that information and we try to actually generate a solution, basically, that indicates in which order the turbines have to be serviced with the spare parts. Of course, the aim of the objective used by the optimization models and the intelligent computational methods is the increase of journey efficiency. The algorithm optimization models we use basically are very mathematical, so they involve an objective, which means what do you want to actually, or a goal, which says what do you want actually to minimize. Of course, in the case of WASP project for the routing of the autonomous vessel, we want to minimize, as I said, the transportation cost. And then we take that and then we build the constraints, part of the optimization model, constraints around as I said, the load that is actually the load constraints of the vessel and the time windows, and as well the fact that the vessel has to leave from the base, come back to the base. We then use computational algorithms to come up with a kind of the best solution, which will indicate in the best order in which the vessel has to visit the turbines to deliver the spare parts. That actually solution then is passed to L3 Harris, to James, as he was saying, to actually plan the navigation of the vessel. The computational intelligent methods are in some way artificial intelligent methods, because what they do, they use some kind of a decision-making process, an iterative decision-making process that actually goes through thousands and thousands of solutions. Then it picks up the best solution from that space. They are very complex algorithms, but the good thing about these algorithms, they are very efficient and very actually fast to find solution. We have done some analysis, part of the WASP project, and we found that these algorithms take milliseconds to actually generate a solution, let's say for 100 of turbines that have to be serviced. And does it clarify?
Yep. No, that's great, Jamila. We've had a question in from one of our delegates from Amir, who asked about predictive analytics to drive operational efficiencies.
Yeah, of course. Yeah, of course, that predictive analytics is used because, as I said, you have to take into account that the route is actually a real-time route planning. It's not static, so it has to take into account the fact that uncertainties we have used predictive models and stochastic models to actually take into account the stochastic nature of these kind of problems of route planning. Because information is fed into the algorithm and the route is actually updated depending on the new information fed into the algorithm to generate the route.
That's brilliant. Thank you very much, Jamila, and thanks very much, Amir, for that question. Keep the questions coming, please. I'd like to ask Steve Pears. So you know, let's envisage you know, a number now of autonomous vessels or utilizing University of Portsmouth's algorithms to decide where they're going to go. From a marine coordinator's perspective, so we're somewhere onshore, you know, we've got a marine coordinator sitting in a darkened room with a number of screens in front of them. Can you talk us through what's going through their mind? What's the thinking processes that's going through their mind? What do they need to do to maintain control of these sort of operations?
So within this within the system that we looked at here, one of the reasons why we were looking at automation was to reduce the safety. In fact, it was one of the key criteria from our project sponsor that dropped objects was still one of the main safety issues for the offshore projects. So in a way, what we were aiming for was trying to maximize the time that technicians are on the turbine carrying out the repair. So from a control center, we have to look into the future and try and work out what is that control center going to look like. So the first steps that we took on this project was to look at how we manage the cargo. Now that actually brings it, really what we're doing as the offshore industry progresses, we're integrating more and more. So the cargo part would be interfaced with the stores planning. So when the work is being planned, that work is being planned and sent into C Planner. C Planner can then interface with all the different aspects to understand where the cargo has to be delivered, and it can basically plan for that cargo to be on Aaron's vessel, and we can instruct, we can take the information from Portsmouth to say what is the route that we have to carry out, and we can inform L3 Harris's system on the routes that the system can take. So in a way, we are trying to automate quite a lot of it. So a lot of the control center functionality will move over to more of a monitoring to ensure that the autonomous vessel is doing as it's planned to do. And one of the things that when we carried out the interface work with L3 Harris, there are points where the control center person can come in and stop a delivery if they feel that delivery is going to fail or the conditions have changed. They can basically send a command to the vessel, and the vessel can either hold station or carry on to the next location. So in a way, we're making a control center person think about a lot more activities and how it integrates with other parts of the offshore wind farm business. But we're taking some of the actions and automating some of those actions away from the control center and marine coordinators. So it becomes much more of a monitoring and basically stepping in if there is a problem. Simon, is that enough for that question, or would you like me to elaborate?
That's great, Steve.
Okay.
And just sort of thinking ahead, so we've talked exclusively so far about fixed bottom offshore wind.
Yeah.
Some of us will be aware that the energy demands for the UK are driving the need for more extensive offshore wind, which will be delivered on floating platforms. What do you think are the prospects for autonomous vessels in the context of floating wind?
Floating wind, we're working on some projects at the moment in relation to floating wind, and it just makes unfortunately L3 Harris's and Aaron's problems maybe one step higher, because instead of having one floating point and one fixed point, you now have two floating points. So you have to look at everything relative to each other. So if you're trying to stay on station, you have to stay on station relative to the other floating point. Now, this isn't new technology. This technology has been used in oil and gas. And really what's moving forward at the moment is looking at how to do this with walk-to-work systems. So your Ampleman and your Uptime walk-to-work systems, which are being used a lot in the fixed bottom offshore projects. They then have to work out how to still stay attached to the transition piece or the foundation whilst both are moving to some degree. So there will be a further challenge. Maybe I can hand that over to Aaron and James to maybe add their points on the floating industry.
Yeah, great. Aaron, perhaps you'd like to go first? Aaron, are you there? Unmute. Or James, perhaps you'd like to pick up then.
Well, I think Aaron's going.
Yeah, I can go. Yeah, sorry, I was on mute.
Oh, there we
So,
are.
yeah, that's fine. Yeah.
Thank you.
Yeah, thank you. So this is about the prospect of autonomous vessels in the context of floating wind.
Yes.
Question. Yes. Yeah. So I mean, in terms of I mean, in terms of a market outlook, I wouldn't have any numbers to hand for that, but definitely we've seen as part of this project, definitely one thing is the feasibility of using an unmanned surface vessel, what we call it as an autonomous surface vessel, to kind of come into the O&M operations or O&M sector and deliver literally the cargo and kind of complement the existing vessels in there. And that in itself is, as the project has shown, is a good start, really. And don't think it's quite disruptive, but it's actually going to, if this is going ahead, then it adds a new dimension in terms of improving the safety of operations and the efficiency of operations, hopefully. And as you will come to later, Simon, you show that there are cost benefits too in the long run. So for these, and you definitely see as a general thing that the vessels are scaling up. The vessels are becoming bigger, the autonomous vessels, the unmanned vessels, that is. And that would mean that there would be influx into every sector. And I'm sure the autonomous, where the wind farm will also follow suit in terms of an adopt, would be one of the early adopters of this technology. That's my feeling.
Okay, thanks very much. James.
Yeah, I think the floating side of it, it is going to create more challenges. I think the larger vessels are going to be needed to support those technologies due to larger sizes of turbines. I think a lot of people are talking 15 megawatts plus for the offshore, for the floating side of things. So yeah, I think that could create a whole range of new challenges. But also there is the potential benefit that as both things will be floating, there might be a reduction in amplitude of the difference between the two vessels. So that could be a benefit, but we don't know until we've got widespread floating, well, not widespread, but at least a couple more demonstrators of the floating offshore wind that are accessible to these sorts of systems.
Okay, brilliant. Another sort of question that's come in is, you know, we're not going to sort of replace manned vessels overnight with autonomous systems. You know, we can envisage a sort of a gradual integration of autonomous systems or uncrewed vessels in with a manned fleet. But I can imagine, you know, some skippers on vessels could be a bit antagonistic and sort of, you know, try their luck to see how good the autonomous vessel is at staying out the way. Do you envisage those sort of issues arising in the future? You know, James or Aaron, you know, how do we manage a mixed fleet of both manned and unmanned vessels?
I think part of this is around the messaging. There is obviously the general concern around mariners and things that are going, well, these autonomous systems are coming for our jobs, but that's just not really the case. We're trying to help the evolution of the marine offshore industry to develop into the future and provide jobs for those very mariners in a safer, more hospitable environment. That's the kind of the goal of this, is we're still going to need mariners. They're still going to be needed to do a whole variety of different roles within the control and operation, but maybe not at sea. So I think that's going to be a challenge. Our experience is most of what we've seen on the water certainly is not antagonistic. It's more curiosity. That's generally down to our history of producing little yellow boats, and people go, what's that little yellow boat doing? It doesn't have people on it. I think by the time we get to deploying 20, 30 meter vessels into offshore wind farms, it's going to be relatively clear what the vessels are doing and everyone will understand it. So I don't particularly see it as a big challenge. It's something we need to message clearly, and also make sure that we're supporting mariners into the next generation of this industry.
Okay, brilliant. Another question that's come in is about, do we envisage seeing autonomous crew transfer vessels in the future? I'd open that up to any of the panelists who've got a view on that. Maybe Aaron, what are the issues? I mean, we've got a vessel at the moment that doesn't need a crew. You've made provision in terms of a sort of shelter space for maintenance and things like that. But if that vessel then needed to carry passengers, so to speak, you know, what are the challenges that we're thinking about there? And is this something that, you know, we'd see in the next, say, you know, 4 or 5 years?
Oh, it's difficult for me to predict as to when that would happen, really. But in terms of it from a designer perspective, for the vessel designer, so I think from this vessel to transition it to something that will carry crew wouldn't be too much of an issue. It would add more steel work to it in terms of more compensations and accommodation for positioning and catering to the crew. So that is one. And because by nature of because for this vessel, when we made it unmanned, we needed to provide for the provision of maintenance, for instance. So we had to have we haven't done away with any of these what should we say, the load line related safety measures for crew. For instance, we have retained that, and that also had the added benefit of protection of the cargo. And I suppose also if the maintenance crew had to be on it in the middle of the sea for some emergency maintenance operation. So from that aspect now, but in terms of if crystal ball gazing into about that, whether the crew transfer vessel will come, I would have to take the project view on it. It'll be further down the line, really. I think we'll have to see adopt what shall we say, put the safety and the reliability of the unmanned vessel operations first there before we actually take crew on it, and so that'll be a slightly more, what shall we say, time on it. Way of doing it, so that safety has to be there. The demonstration of that and the reliability will have to be shown in the sector before people will step on it, I think.
Okay, thanks, Aaron. Steve, do you want to come in there?
No, I think Aaron just covered it towards the end. I thought you might miss out, but the reason why we did not take that extra step and do crew transfer vessels was we thought that the industry would need the autonomous vessels to be proven. And we looked at a way of proving autonomous vessels, and we thought that the cargo handling and management and the benefits that go along with it was a good way of proving autonomous vessels could be reliable prior to putting people on them, and and also challenging some of the regulations around transferring and carrying people offshore. So as Aaron said, it was a good step towards proving the autonomous vessel.
Do you think that's one of the sort of remaining challenges in? I mean, the technology looks like it can cope, but it's down to sort of human nature, human acceptance.
It's definitely, if you think about most airplanes that take off, most of the time they're in autonomous mode. We do travel the world mostly in an autonomous mode. So I think, it's the same challenge as saying, drive an autonomous car. It's a new thing to us. The technology is moving forward and is not far away. But I think you have to prove it to people in steps. I think probably James has maybe got more experience on this, and maybe it's for James to comment on as well.
Yeah, I suppose the not wishing to put words in James's mouth for this, but I suppose a lot of the technology will come from other sectors, you know, autonomy delivered in aerospace, in defence, through automotive as well, will find its way into you know, sort of maritime applications. What are your thoughts, James?
Yeah, I think we're broadly trying to learn from the widest range of technologies possible. The challenge is actually, to a large extent, the marine environment is, from a sensor point of view, a lot more unstable than either the air or land environment. Generally in the air, your platform is relatively stable, with the exception of turbulence, but the large proportions of the time it's quite stable. So the way you can detect things and monitor things is simpler from that regard, and also you're operating in a very controlled way. Excuse me. You're operating in an extremely controlled way, so that means that you are able to plan better. And as we were saying earlier, autonomy is all about planning. In the automotive environment, it's a bit different. Again, you're very much more stable, so you're going to be going down a road. Roads in general are quite flat, which means your sensor performance can really be optimized for that environment, although you're going to have a lot more contacts than you probably would in a marine environment. But in the marine environment, certainly in the vessels we're coming from, and even on the sort of vessels the size that Aaron has been proposing, there is a lot of movement, and you've got to prepare your sensors for that level of movement. And that is part of the real challenge of that, and how we can adopt that side of it. With regard to adoption, I think that adoption is I think for the general public is relatively easy, because most marine operations are kind of a bit out of sight, out of mind. So I don't think that's the challenge. It's really getting people like Ørsted on board with the plans and how we do it, and then at a lower level, the people who have actually got to operate the vessels. But I think in general, that's a hearts and minds thing that's being generally progressed pretty rapidly at the moment, actually.
Okay, super. We've had a question come in from Tim Moran. Morning, Tim. Hope you're well. Tim's asking about the strategy for unloading components from a vessel to a turbine, either fixed or floating, using autonomous vessels. And he's saying, is it anticipated that a vessel would dock up to the turbine to enable lifting operations, or still remain remote and use large cranes? And in the context of floating wind, would these autonomous vessels be providing large component replacement, for example, blade or gearbox replacement? And if I just flick back to previous slide, I don't know when you joined the session, Tim, but the concept that we developed in the WASP project was for a autonomous vessel of around 29 meters overall length that was able to stand off from the offshore wind turbine structure, and then with a 1 ton sort of lift capacity, it was able to drop palletized spares onto the transition piece without using the davit crane that's on the transition piece. And I think our proposal would be something similar, maybe bigger, for floating platforms, obviously depending on the height of the platform. I think in terms of large spares, blades and things like that, I think in the future, you know, I'd stick my neck out and say that anything's possible there. Maybe the technology isn't quite ready. I think it's doable. But in terms of the floating platforms in particular, cranes with that lift capacity and that reach capacity for 50 megawatt turbines on a floating wind platform out in the Celtic Sea, there's some big vessels and structures, and I think that's more about the operations and maintenance strategy for floating offshore wind platforms. Are they maintained offshore, or are they brought into shallower, quieter waters for sort of deep maintenance? Don't know if our panel's got any views on that.
I can, Simon.
Yeah, Steve,
I can.
Please.
We focused on the sort of day-to-day activities. So the reactive maintenance and the ongoing planned maintenance during the year. Obviously, when you get to the summer period, you have your maintenance schedule for your large swap outs and repairs, where you might bring in a jack up or an SOV. So generally, we didn't try to focus on that, simply because, same again, we wanted to prove it at a scale such as a 1-ton load first, and generally where you're bringing those vessels in to do the heavy lifts, they tend to be manned vessels at the moment, and I don't see that changing until we've proved autonomy at this scale first. Yeah.
Okay, brilliant. This is all well and dandy, this panel sort of talking amongst itself and taking questions from delegates, but I suppose that people will want to know, who are the stakeholders that we engage with during the project, what were the issues that they saw were important, and we had a number of stakeholder engagements, and we actually towards the end of the project we ran 4 stakeholder events where we actually went through some synthetic scenarios. We had a good look around the workshops at L3 Harris, and we were able to sort of really sort of pry and sort of poke these systems to see how well they worked. But talking about the sort of the types of stakeholder engagement we've had, maybe on the regulatory front first, James, maybe you could sort of just give us a summary of some of the discussions that we've had with the sort of Maritime and Coast Guard Agency and people like that.
Yeah, so we're in quite the fortunate position that the government, through the Industrial Strategy Challenge, is very supportive of autonomy and of allowing and enabling UK businesses to develop autonomy. And that's been pushed down through the MCA to say to them, like, come on, you need to engage with this industry and you need to support them in their endeavours. And they've actually been very forthcoming. They've set up a marine autonomy team that we're well engaged with. And they're really looking at being a good regulator. So looking at how we can do this safely, as safely as possible. So it's good, strong engagement at the moment, and we're looking to continue that and moving from currently, which is a very case-by-case kind of regulatory monitoring, I'd call it. I'm not sure it's really approval yet, and then help them move towards clear regulations that enables a much wider adoption from a greater range of parties of the autonomous technology.
Brilliant, thanks, James. Jamila, if we cast our mind back again to those stakeholder events that we held, there was a lot of interest in the algorithms that Portsmouth had developed. Do you want to sort of give us a summary of some of the discussions that you had with stakeholders around those algorithms?
Yeah, I mean, the stakeholders were very interested in the optimization part of what we've done for WASP, and mainly how the intelligent computational methods, their strength in actually generating solutions in such dynamic and complex environments. So yeah, I mean, there was some of the stakeholders were raised the issue around if I have maintenance and a maintenance task, and I have to deliver cargo to a set of turbines. They were interested in how can I make a decision, the optimal decision actually, on the number of vessels, the autonomous vessels, or in general. They were applying that even for the vessels used currently in offshore wind farms, the crew transfer vessels. They were saying, how can I define the optimum number of vessels I need to deliver the cargo for the turbines? And the other aspect, which is very interesting as well, in the WASP project, we have mainly focused on the use of one autonomous vessel and the delivery of spare parts to the turbines. However, we will see more potential of these algorithms and their strengths when we consider a fleet of vessels, autonomous vessels, because we need to bear in mind that the capacity of the load of the vessels with cargo is quite limited. So if you have one single vessel to service the turbines with the spare parts, you need to take into account that that vessel has to come back to the base, then load and then deliver. But if we have a fleet of vessels, that would be even more efficient in some way, because you can plan in advance depending on your maintenance tasks. You can plan on the number of vessels you need, autonomous vessels you need, and you can as well plan we call it as well, artificial intelligence, a swarm of vessels that will be used to efficiently deliver the spare parts to the turbine. So these aspects of optimization and efficient computational methods were really of interest to people, to the stakeholders who attended the event. We've used them as well in the past, to be honest, on another project, more for the defense sector on the route optimization, and James Althwy-Harris were involved in that. So they've been quite popular, I have to say, and it shows what makes them actually popular is their strength to deal with the complexity of thousands of solutions, and the fact that they take seconds to get the solution generated. And the fact as well, it was one of the questions raised earlier, is the strength of these algorithms to handle stochastic data, because these algorithms, they are stochastic in nature, and the repetitive way how they generate the solution makes them ideal for these kind of problems.
Okay, brilliant. Steve, I don't know if you wanted to come in on the stakeholder discussion. Otherwise, we've got a question.
Yeah, just quickly on the stakeholder side. One of the stakeholders that we got involved was an insurance company, because at the end of the day, you can come up with as bright ideas as you want, but if you can't insure it, it ain't going to happen. So it was bringing along an insurance company to really tell us what the challenges were, feedback to us. If we're taking a vessel out there with 41-ton box of spares, how do we overcome the challenges that an insurance company would need to to basically be able to ensure the operation in the vessel. So and I still think we talked about the challenges, but there are still steps to take along that route to get the insurance companies on board with insuring a totally autonomous vessel.
Yeah, absolutely. Had a question in from Michael King. Michael, thank you very much indeed, and good morning. Michael says, do we see a faster route to field trials and proof of concept with a lean manned option? And he cites an example, remote command and control of the vessel, but with a small crew on board the vessel for cargo monitoring, emergency response. Any thoughts on that? So actually having a small crew on the vessel, on an autonomous vessel, that's there just to make sure that things go okay. Is that a faster route into proving this sort of concept?
I think from a point of view of cargo handling, that's definitely a part of it, because one of the critical technologies here will be the crane, and removing entirely the manned element from that is going to be really challenging. And then there is the other side of it, is that once you start going above the 24-meter small boats code, having the ability to satisfy things like SOLAS and other elements of the current rules of the sea will definitely speed adoption, because at the moment the IMO is going through how it's going to enable the use of autonomous vessels, but they're not there yet, and it could be a number of years before they are. So yeah, there is a level of, on the larger vessels, a lightly manned solution could help.
Yeah, I agree. Actually, I think that's more likely the way to go. And just a follow up from Tim Warren. His question was about the sort of docking and cargo transfer, and just thanks us for the response that we've given. And you know, interested in the thoughts about operations and maintenance for larger cargo replacement, which I think are entirely feasible. I think it's just we need to look at the you know, the way that we do these sort of things. I'd like us to move on and just think about just quickly. We did that slide. WASP 2 follow on. So as a consortium, we're continuing to work together, and we're sort of looking at the what next should we do. And on this slide, these are broadly the themes that we're putting together in a proposal. If there are people out there who've been inspired or interested in what we've talked about, then we'd be more than interested to hear from you. If you'd like to be involved in some shape or form in follow-on project. But let's just talk about, and you know, let's get our crystal balls out in a sense, and think about what sort of things we need to do in the future. What are the important areas for development? And I'll probably start off with Aaron and just talk a little bit more around what we need to do around the vessel. Maybe then James to say, you know, where do we need to go to on command and control for these systems. Then I'll ask Steve to talk about the sort of marine coordinator, end-to-end cargo delivery side of things, and then Jamila in terms of logistics. So Aaron, can you give us a very quick overview of what you think we need to look at going forward?
I should do, Simon. I'll start with the robotic arm or the crane, because I spoke a little about it earlier. So the motion compensated crane, that development of that, or the demonstration of that, will be the key in terms of development for the next phase. So we need to demonstrate with the prototype. This crane has got 5 degrees freedom in a way, with roll, luffing, folding, extending, and the pickup and delivery as well. So that's it's a complex piece of kit. And then there's the additional aspect of compensating for the drift of the vessel, in addition to the first order motions. So there's a lot in there to be demonstrated and tested as well. But that is, again, it is en route to the market, and prototype testing is the next way that we think will be the route to market for that one. As you know, the design that we've adopted is not off the wall. It is something that's very similar to what exists in the industry. It's been made bespoke for the function that we're looking at, and our initial feasibility has kind of put it in the space of components that's available, be it the cylinder, preliminary specifications, the design stroke, or the flow rates and the power consumption, all of which have been found as feasible. So in terms of so that's where. And then you're looking at the targeting system as well. There's some mention about sensors and their accuracy that you mentioned earlier, that you need to pick up a cargo from the back end of the vessel, slew around, and deliver it onto the transition piece, and then reverse that process and compensating for motions all the time as well. So that's there's an element of targeting system design that will need to be done as well, and so that's on the crane development. So that's, in summary, that will be a prototype testing of the crane to show its motion compensation, drift correction, and the cargo pickup and delivery capabilities. On the vessel side, I don't think we would need to go for prototype testing. One is to minimize the cost implications for those, and being that it's also the vessel design, it will be more in the domain of well-entrenched design processes. So there we will be looking at, as also alluding to the earlier question about lean manned vessels, because as James said, the moment we go around unmanned, then we'd have to have a complete rethink of the system from pure risk-based assessments about the removal of personnel from the maintenance side of things. So it'll really be useful to have a system design, block diagrams and the philosophies, and to the extent of developing the various machinery systems, the piping systems, and the electrical systems. So that's the next step on the system side. On the vessel side, we'll be refining the hull form. We'll be looking at drift and drift assessments, and also on the structural design of the integration of the crane. And of course, moving on with the stability assessments and going through the spiral, design spiral, refining it further. So that's on the vessel side.
Sharon. James, on the command and control side, what do we need to do?
Well, the good news is that a lot of the command and control stuff is either completed, tested and done, or will be in the very near future. We've been developing these vehicles and operating them in environments not dissimilar to this for the last 20 years. So I think we're very confident in the delivery of the vessel autonomy and navigation solution. Now, as we talked about earlier, there is levels of autonomy. So it will be a case of how we take the autonomy to the next level to enable multiple vessels to be operating with reduced OPE supervision. Enabling that regulatory compliance is going to be critical for this. But even today, there's vessels operating in ports and offshore that use this technology successfully in these environments. So I don't see the navigation or the autonomous vessel side of it being a significant challenge. There is a level of the regulations as we get into larger vessels, but the principle is proven and working.
Brilliant. Thanks, James. Steve, do you want to very quickly tell us about sort of end-to-end cargo management logistics?
So within this project, we did integrations, software integrations with L3 Harris and Portsmouth University to work out how to pass the information, the data through for the planning and cargo management. But that's very that's an R&D scale where we're looking at sort of passing through one at a time. So realistically, it's taking that further forward and trying to challenge it in a real life environment where you're not just talking about one or two cargo deliveries. You're challenging it with 20 or 30 a day. So there is more integration to be done, and also to put the sort of controls in front of the client. And with Aaron is and Holder are developing the robotic arm, but some of the information that we need to know is about the successful delivery of the cargo itself. So there'll be, as Aaron is developing the targeting system for the delivery from the robotic arm, we will need information coming back from the Holder system to prove that the cargo's there has been successfully delivered, and the engineers can go onto that turbine and carry out the repair work.
Okay, brilliant. And finally, Jamila, tell us a little bit more about algorithm development, probably for sort of multi-vessel operations.
Okay, so our work in this phase 2 will focus, as I said earlier, on the implementation and the design of swarm optimization algorithms. There are quite as well very successful algorithms that have been used in road transportation, and where if you have maintenance tasks, and what these swarm optimization algorithms will do, they will actually consider a set of vessels that have to be used to service the turbines with the spare part. So the strength of the swarm agent-based algorithms, which are again an artificial intelligence, it's an artificial intelligence method, their strength is their ability to collaborate and coordinate their actions, and that's really, really important in offshore wind farms, because they're quite due to the dynamic nature of offshore wind farms. So you could see this fleet or swarm of vessels actually going into the wind farm and coordinating their operations to service the spare parts, which means it could take into account any unforeseen events that haven't been considered initially when the routes were planned to service the vessels, and they can in some way collaborate and cooperate their actions to make sure actually the delivery of the spare parts actually happens. So this is our future work for WASP 2.
Okay, that's perfect. Thanks very much, Jamila. So we're actively looking at WASP 2. We're pulling together a proposition. If you're interested in talking to us about that, then please do get in contact. We're drawing towards the end of this event now. I hope you've enjoyed it. It's really stimulating. It's good to chat about these things and sort of share ideas and learning. So thank you very much for listening today. I hope it gave you sort of food for thought. And thank you very much for all the questions that have come in. I'd like to thank the panel. I'd like to thank Steve Pears, Managing Director of the C-ROC Group, and Jamila Awihad, Professor of Operational Research and Analytics at University of Portsmouth, James Cowles, Business Development Manager at L3 Harris Technologies, and Aaron Pillar, Principal Naval Architect at Holder. And a thank you to our sponsor for the original WASP project as well, to Ørsted. You can see on the slide there my contact details, and I can pass on your details to any of the panelists. There's a WASP information page on the Catapult website, and we will be emailing out the video to delegates, and that video is also available on YouTube. The roadmap as well is available on the WASP information website. So if you've got any other further questions, please do get in touch, and we'll get right back to you with answers. So that's it from us. Thank you very much indeed. Thank you for listening, and stay safe and enjoy the rest of the day. Thank you very much indeed. Bye-bye.
Thank you.